So I'm just going to do a weird looking arrow here. Okay. I'm going to write it smaller. But what do I have in front of those? Well, actually, I'm going to write the reaction. So do we know what's going to happen as a reaction? I've got methane, CH4, nitrogen, and oxygen. What do I get as a byproduct? So these are my reactants right here. This is air. This is air. And this is methane. What is my product? Or what are my products? So the first product is I'm going to react hydrogen with oxygen. That's what I'm after. So my first product that I always want to think about is water. Water. I'm after hydrogen. I'm not going to react. I'm not going to get energy after the carbon. I'm after this specifically. So, and I'm using hydrogen or hydrocarbon. That's why it's called hydrocarbon. You're after this reacting with this. So the first byproduct is water. Now I don't know how much I'm going to get as water, so I'm just going to put a coefficient right here, B. Okay, plus somebody else said CO2. Well, I could have, well, CO2. I was going to use C, but that's bad. It's going to look CCO2. So let's make it D. So at least you understand why we skipped out C as a coefficient. And what else do I have? Nitrogen. Nitrogen is not going to react, it's just going to come through. Now, this is assuming no dissociation. I'm not getting any NOx or so forth. So I'm assuming I have a clean combustion process. So when you're talking about emissions, you can control emissions through optimizing your combustion. However, right now we're assuming clean combustion, so we're going to say E and nitrogen. Okay, so how do I know my atomic balance in terms of these coefficients? I could say, well, I'm putting in 1 molecule of carbon, right? There's a coefficient right here. What is that coefficient? Just 1. 1 multiplied by CH4. So 1 multiplied by how much carbon do I have? 1. Right? So carbon, C. Yeah, I'm glad we didn't use C. That made it confusing. So C, how much moles of carbon that I'm putting? Just 1 moles of carbon. Okay? And if I look at the other side, whatever I put here in terms of my species is going to be conserved. Again, remember that no human has been able to generate mass out of nothing. So species are conserved, like we mentioned, I think last class, some of the conservation of species. So if I have carbon, what's going to go on the other side? 1 carbon, right? So what does that tell me about D? 1. Very good. So from this I could say, well, D is equal to 1. Very straightforward. Hydrogen. Hydrogen. How much am I putting in? 4. So from 4, I'm saying 4 is equal to how much here? 2B. Because CH4 is an easy one. Start doing octanes or jet fuels, you will get different carbons and hydrogens, and you're going to get different numbers. So right now it's clearer, but it's easier. Write the equation first, and then figure out what B is equal to. So based on this, B is equal to 2. Very good. All right, so now what do I have left? So I've gotten that, oxygen. How do I get oxygen? Well, it's A multiplied by 0.21 multiplied by what? It's 2 molecules of oxygen, 2 moles of oxygen, is equal to, now I have 2 oxygens here. Well, it's equal to by, it's a linear equation, so I'll say B multiplied by 1 right? I'm just going to write it 1 plus D multiplied by 2. So from that, I could say A is equal to B plus 2D divided by 2, 0.21. And from that you get 9.52. And now you know how much air you put with a 1 mole of CH4. What do I have left? Nitrogen. I could figure out how much nitrogen I have. I will say, well, nitrogen, it's A multiplied by same principle, 0.79 multiplied by 2 moles is equal to 2 or E multiplied by 2. So from that, E is equal to 7.52. And now I know everything about my reaction here. Very simple and straightforward. Now, do you understand why? Did I use the mass or molar-based formulation to compute my coefficients? Moles. Now, if you try to do this with mass, how hard will it be? And it's not hard, you can get it, but how difficult it is to get these coefficients. Because now you gotta go take the mass of carbon, how much it weighs. Mass of hydrogen multiplied by 4. The mass of nitrogen. The mass of oxygen in terms of kilograms. So it becomes a not an easy process. You could get the same answer, you're gonna get the same answer, but with the mass-based version, it's not friendly. So that's why chemists prefer this, because they could just bookkeep it. They're like, I don't care about my units, I'm just gonna use it as a moles-based version. And that's how they get this quicker. So we'll see as the semester progresses. I'm gonna take a survey and see which one you prefer. I'm interested in seeing it, because I still think in the end, engineers end up choosing the mass-based version. We'll see. Okay. It's funny because in the end we end up choosing the harder way. Engineers will end up doing, because we want to be precise and we want to be able, because this is like, oh, this is too simple. I got this too easy. If I do the mass version, it'll be a very lengthy process because you have to compute each one and then you make sure your units are correct and then in the end you compute it. But now you can just get your mass fractions and you don't have an issue. So let's write the final equation, what it looks like. So it's CH4 plus 9.52 multiplied by 0.79, nitrogen plus 0.21 of oxygen will give me 2H2O water plus CO2 plus 7.52 of nitrogen. And that's my final equation. So, what do I have? I need to know my fuel-air ratio. So, fuel to air ratio, which is very, very critical with propulsion systems. It's equal to, by definition, the mass of fuel divided by the mass of air. The textbook uses F. Textbook. As you go out, so at Pratt we never used F, we used FA. That's the fuel-air ratio, but textbook uses F. Okay, so for stoichiometric, which that's what we're after, conditions of methane and air, it's the mass of fuel, which what do I have? I have 1 kilomoles of fuel multiplied by my molar mass, MWCH fuel, CH4. So what do I get for, what is the molecular weight? So molecular weight for CH4. Now, I know the molecular weight or the molar mass for C and H, but how do I get it for CH4? So this is very critical because most of you, the first midterm, I would say 90% of the students wrote it on their cheat sheet, but 5% did not. And they should know this automatically at that time by the time of the midterm. So I'll caution you right now. How do I go and compute the molar mass for CH4? Anybody know?
You add the molar mass of carbon and hydrogen, so 12 plus 4.
Exactly, 12 plus 4. So how did I get to that number? It's essentially, so it's plus 4, 16 kilograms per kilomole. So they got to a problem where they needed to know this value. Now, how did I get 16 kilograms per kilomole? Well, I have how many kilograms per kilomole for each individual species that I have. I have C. C is 12 kilograms per kilomole. And H is 1 kilograms per kilomole. So I have C that is 12, so they had this at their cheat sheet, but they could not compute this value. And once you don't know how to compute this value, how are you going to get your fuel air ratio? How are you going to get stoichiometric conditions? How are you going to figure out if I'm asking you to figure out the MA, and I'm giving you F, for example, how are you going to go and figure that out? You needed to know this. They had this, but they couldn't figure out this. It was a small percentage, but I'm cautioning it right now, because during the exam, I felt bad for them because it's an easy thing, and I could say it, but it's not fair to the people that already, most of them, as I said, 95% of the class already knew how to do it. So I'm emphasizing it right now, okay? So how do I get to this? Well, it's 12 plus, I have 4 kilomoles of my hydrogen, so 4 times 1, 4 plus your 12. So if I give you propane, does that impose a threat to you? No. If I give you jet fuel, and I tell you how much C, X versus Y, it doesn't matter. You can figure it out. So if you've seen a fuel that you don't know it, you can compute this because as long as you understand this and do this. So you have a cheat sheet, you could write an example if you wanted to, but it's critical to have it. All right, so from that, can I get my mass of fuel? Yes. From this, it's 1 kilomole multiplied by my molar mass, so it's 16 kilograms of fuel for this stoichiometric condition. Now, MA is essentially mass of air needed to burn 1 kilomole of fuel. So MA is going to equal to my molar mass, the number of moles of A, air, multiplied by the molecular weight of air. Now, air. Let's do the molar mass of air. How do I get the molar mass of air?
79.2% nitrogen.
Is this a specific species? Is A a specific species?
Mixture.
No, right? It's a composition of what? Nitrogen and oxygen. So what did I do last lecture? I spent time doing non-reacting gas mixture. So from this, what I said, it's equal to the summation of my mole fraction multiplied by my molar mass. So from this, I have what? I have 0.75 of nitrogen, so MW nitrogen, plus 0.21 of oxygen. This is why we were doing all this stuff last lecture. So now, from this, what do I get? I get MWA is equal to 28.84 kilograms per kilomole. I think in the book it will be like 9.7 or something like that. It really depends, but it's just 28 something. Okay, so now that I got this, can I get the mass of air? Mass of air is equal to my number of moles of my air. So what do I have? I have Na. What is Na equal to? Very good, 9.52, which is this. So I can show it to you right here. The one that we computed, which is our original A. 9.52 kilomoles multiplied by 28.84 kilograms per kilomole. And from that, what do I get? I get 274.56 kilograms. So now that I got MA and I got my MF, the mass of fuel, mass of oxygen or air, now I need to figure out my fuel to air ratio, which is my F that I'm after. I'm gonna make it lower F. Well, that's equal to simply 16 kilograms divided by 274.56 kilograms. And from that, I'm going to get 0.058. And that is the stoichiometric FST, stoichiometric fuel air conditioning. So that means I took my fuel, I took my air, with whatever oxygen it has, and I completely burned all my fuel and oxygen and converted it to a complete reaction of water, CO2, and nitrogen just passed through the reaction and didn't do much. It's critical, but it didn't do much. It didn't react. It's critical in terms of it's actually a working fluid, but it passed through. So, from that, what do I get out of this? This is the ideal combustion process. Because I've taken all my fuel, and I've taken all my oxygen that I have in my air, and I completely reacted it. Let me put this. I don't have excess fuel coming out. I don't have a little bit of CH4 coming out. I don't have a little bit of oxygen that is remaining. I'm going to do this shortly. What if it's less or greater than the stoichiometric condition? But I burn everything here. And by burning everything here, that's the ideal combustion process, and therefore I got my stoichiometric condition. Now, here's a quick hint, trick, whatever you want to call it. That value, for whatever fuel you're working with, it's not going to vary much. So that 0.058 is going to be anywhere from like 0.065 to 0.045. If you get a weird number out of that range, you know you've done something wrong. Okay? So that's sort of a hint if you run later on and you're trying to solve the problem, or you're working at Pratt or GE and you get, let's say you get 0.1, no, just go back and recheck. Something is not right. That's the idea. It has to be, most likely, given all the fuels I've seen, I've never went beyond these ranges. Okay? So, if you're around, if you're out of that range, you're just going to start to see, just quiz yourself, does it make sense? Go back and recheck your calculations. Questions?
So that's just the stoichiometric fuel air conditioning.
Yes. No. That's for all fuels. So that's a good question. So this is not for methane, right? We already know methane. Methane is this.
So that's
Okay, so this is fixed for methane, CH4. That's a good question. This is, I'm talking about all fuels outside. So this is jet fuels, gasoline fuels, propane fuels, whatever fuel you're using, most likely it's within that range. It will be, well, with bio-based fuels, you might go low, but remember it's the second decimal point right here that defines it. If you have a slight variation more than this, if your first decimal point, use that as an indication that I'm doing something wrong. Let me recalculate again and make sure I'm doing it right. You might be working with a weird fuel. I don't know. 10 years from now, we might discover something new that you're working on, and it's not there. But I'm telling you, in terms of just general fuels that we have today, that's the ranges that we have to play around with. Sometimes it could get lower, but not that low. Question?
Yeah, so what kind of fuel do